In Chapter 4, we will start talking about distributions of random variables. Chapter 4 specifically discussed discrete random variables. So in this chapter, we will learn how to recognize and understand discrete probability distributions, how to calculate and interpret expected values, how to find probabilities of events within discrete probability distributions. And this chapter allows us to gain a deeper grasp on probability distributions by looking at distributions that may seem more familiar to us. We will practice finding probabilities and applying our knowledge to real-world situations, which will allow us to expand this in our coming chapters talking about continuous random variables. So discrete random variables. A random variable describes the outcomes of a statistical experiment in words. The values of a random variable may vary with each repetition of an experiment. Remember, discrete means countable, so whole numbers, no decimals. So random variable notation, a random variable is denoted by an uppercase letter, such as capital X or capital Y. The value a random variable may assume is denoted by a lowercase letter, such as lowercase x or lowercase y. We will talk about probability distribution functions, PDFs. A PDF for a discrete random variable has two characteristics. Each probability is between 0 and 1, and the sum of the probabilities is 1. Now these two things may seem familiar because they're two of the rules that we had about probabilities in our last chapter. We're going to organize our probability distribution functions in tables. So probability distributions for discrete random variables are easily represented in tables. Here we see our random variable x may be a -1, a 0, or a 5. And we see the probability that our random variable equals -1 is 0.75. The probability that our random variable x equals 0 is 0.2. And the probability that our random variable x equals 5 is 0.05. We notice that these probabilities all add up to 1, which lets us know that we have a complete probability distribution. When a value is missing from a table, we can most certainly find it by subtracting all of the other values from 1. So 1 minus 0.2 minus 0.1 minus 0.15 minus 0.14 minus 0.21 minus 0.13 gives us 0.07. So we were able to find the missing value. Now we can only do this when we're missing one value, but it's helpful to know. We will oftentimes talk about expected values when we're talking about probability distributions. Expected value is the same thing as mean, so you can use these two words interchangeably. So let's find expected values by using our nice table. To find our expected value, we're going to take x times p of x and add all of those up to get our expected value. So for example, if we had the probability distribution function where x could be 1, 2, 3, 4, 5, 6, 7, or 8, with given probabilities here, we could fill in x times p of x for each one. So 1 times 0.13 gives us 0.13, 2 times 0.11 gives us 0.22, 3 times 0.16 gives us 0.48, and so on, calculating for each of these. Then to find our mean or our expected value, we will add this final column that we just created all together. So adding that all together, we find the mean or the expected value is 4.37. Find the expected value of the random variable. We're given some probabilities, we're given some scores. Notice that our x values, our data values, are the scores, and p of x is the probabilities that are given. So our expected value or our mean is 2 times 0.01 plus 8 times 0.05 plus 9 times 0.05 plus 10 times 0.3 plus 12 times 0.25 plus 13 times 0.25, which is 10.3. So let's talk about standard deviation. We saw a couple chapters ago that standard deviation was a little bit more challenging to calculate, and we used the table last time we did it. We're going to go ahead and use a table again this time. First, we're going to need the mean. Then we're going to make a new column for x squared times p of x. Now this is the same times x times p of x, so we can just multiply the first and the third columns. And then we're going to use this formula. Now this formula gives us sigma squared, which is the variance. The variance is the square of the standard deviation. So we would then need to take the square root in order to have the standard deviation. So as we're doing these calculations, we need the mean. We need x squared times p of x. We will add up all of the x squared times p of x, then subtract off the mean squared, and then take the square root of that answer. So let's look at an example using one of our last examples. We see x, we see p of x. We've already calculated x times p of x, giving us our mean. So let's calculate x squared times p of x. So x squared times p of x is x times p of x. So 1 times 0.13, 0.13. 2 times 0.22, 0.44. And then 3 times 0.48 gives us 1.44. 4 times 0.68 gives us 2.72, and so on for the rest of them. Then we would add this final column up. So we have 24.23. So the variance is 24.23 minus 4.37 squared. So that's 5.1331. So it means the standard deviation is about 2.27. Now keep in mind, variance is sigma squared, so variance is equal to 5.1331, and standard deviation is 2.27. So example 2, consider the discrete random variable x given in the table below. Calculate the mean, variance, and standard deviation of x. So the mean, x times p of x, and add it all up. We get 16.1 for our mean. Variance, we want x squared times p of x, so 5 squared times probability of 5, 8 squared times the probability of 8, 17 squared times the probability of 17, 20 squared times the probability of 20. Adding that all up, we get about 293.9. So that means the standard deviation is the square root of the variance. So the standard deviation is approximately 17.1. Now if you're asked for the expected value is the same thing as the mean. So your expected value is 16.1. Now there are some special distributions that we are going to talk about in this chapter. While there are numerous special distributions, we are going to look at just 2 of them together. We're going to look at the binomial distribution and the Poisson distribution. These are both discrete distributions that we'll be taking a look at. As we move on to continuous distributions, we will look at a few special ones there as well. So the binomial distribution, it has 4 characteristics. There must be a fixed number of trials. Each trial can have only 2 outcomes, or outcomes that can be reduced to 2 outcomes, and these outcomes must be able to be considered as a success or a failure. The outcomes of each trial must be independent of each other, and the probability of success must remain the same for each trial. we're going to use N to denote the number of trials, P for the probability of success, Q for the probability of failure. So Q should equal 1 minus P because those are our only two options. So let's talk about some formulas that we can use. The probability that x equals little x is equal to n factorial divided by n minus x factorial times x factorial. And then that fraction is times p to the x times q to the n minus x. The mean of a binomial distribution is n times p, and the standard deviation of a binomial distribution is the square root of n times p times q. If you're looking for the probability that x is less than or equal to little x, you'd be doing the probability x equals 0 plus the probability x equals 1 all the way up to the probability that x equals x. Now, it's not too bad if we're doing the probability that x equals a given number, but if we're saying that probability that x is less than or equal to 6, that means we have to do the probability x equals 0, probability x equals 1, probability x equals 2, x equals 3, x equals 4, x equals 5, and x equals 6. That's 7 probabilities that we have to find. 7 times we're using this first formula here. So it might be nice to find a slightly more efficient way of doing this. Enter your calculator. So many times using the formula is not efficient because instead of looking for the probability of exactly x, we often are looking for the probability of more than x or less than x. Oftentimes the calculator can save us time in crunching these numbers. The calculator knows 2 functions that can be useful. They're called binom PDF and binom CDF. We need to know how and when to use each of these functions. Probability that x equals little x is equal to binom PDF n, p, x. Now some of your calculators will need you to enter these directly. Some of them will pull up a menu when you pull up your binom PDF. The probability that x is less than or equal to little x is equal to binom CDF n, p, x. Notice that these are in alphabetical order. It makes it a bit easier to remember. We'll discuss more about finding these on your calculator in a minute. We need to make sure that we know how to find the correct n, p, and x. So let's practice rewriting the following probabilities so that we could use our calculator. If we were looking for the probability of more than 3, that would be the probability that x is greater than 3. We need it to say either equals or less than or equals. So the probability of x being greater than 3 is 1 minus the probability that x is less than or equal to 3. We're using the complement rule here as we rewrite. What if we wanted the probability of at least 3? That would be the probability of x is greater than or equal to 3. So using our complement rule, that's 1 minus the probability x is strictly less than 3, but we need a less than or equal to. So we have 1 minus the probability x is less than or equal to 2. Notice here that since we have a discrete distribution, the probability that x is less than 3 is the same as the probability that x is less than or equal to 2. We see this fact again when we're looking for the probability of being less than 3. We need a less than or equal. If x has to be less than 3 and it has to be a whole number, the largest thing that it can equal is 2. So that means the probability x is less than 3 is equal to the probability x is less than or equal to 2. Again, this works because we have a discrete distribution. What if we're looking for the probability of at most 3? That would be the probability x is less than or equal to 3, which is how we would need it for typing it into our calculator. Finally, probability of exactly 3 is x equals 3. So we'd be using the PDF on that very last one there. The rest, we would be using the CDF. Now to find these functions on our calculator, if you have a TI-83 or 84, it should look something like this. You see this button called VARs. If you hit second and then hit this button, you're going to go into the distribution menu. Both Binom PDF and Binom CDF will be found underneath this menu. You may have to scroll towards the bottom though. Again, your calculator may pull up a menu for you, asking you for number of trials, probability, and X, or it might just pull up on your screen Binom PDF, and you'll need to enter N, P, X. The comma button is found over the 7 button on your calculator, so it should be fairly handy for typing that. Most newer calculators, though, do have the menu for you, so if you have a newer calculator, you likely have the menu. Let's look at an example now. If a seed is planted, it has a 90% chance of growing into a healthy plant. If 9 seeds are planted, what is the probability that exactly 2 do not grow? So a summary of what we have a sample size of n, our number of trials is n is 9. Our probability of not growing, because that's what we're looking for the probability for, is that 2 do not grow. So the probability of not growing is 0.1, and we're looking for exactly 2. So we're looking for probability x equals 2. So we could use our handy dandy formula, or we could jump straight to our calculator and use the Binom PDF function. N being 9, comma P is 0.10, comma X is 2. Either way, you should end up with the probability that X equals 2 equals 0.172. So looking at example number 3, if a seed is planted, it has an 80% chance of growing into a healthy plant. If 12 seeds are planted, what is the probability that exactly 1 does not grow? Again, we have your summary, and you have 2 different ways you could do it. You could do it with your formula or using the calculator function. Either way, you should be coming up with the probability that x equals 1 is 0.206. Let's look at another example together. A high school baseball player has a 0.286 batting average. In one game, he gets 9 at-bats. What is the probability he will get at least 6 hits in the game? So our number of trials is 9. Our probability of success is 0.286. And we're looking for the probability of at least 6 hits. So that's the probability x is greater than or equal to 6. First, let's rewrite that so that's something a little bit more useful to us. Using complement rules, we can rewrite that so that we have 1 minus the probability x is less than or equal to 5. So that's 1 minus Binom CDF, and entering N, P, and X. Now you can type the 1 minus before going into your distribution menu to find your Binom CDF function. You don't have to though. You can do the Binom CDF function, get your result, and then do 1 minus the result. In the end, you should come up with the probability of getting at least 6 hits in the game is 0.020. Looking at example 4, you again have a high school baseball player. This time they have a batting average of 0.171. In one game, this baseball player gets 9 at-bats. What's the probability he will get at least 7 hits in the game? So we have our summary here. N equals 9, P equals 0.171. looking for the probability that at least 7, x is greater than or equal to 7. So using our complement rule, we end up with 1 minus p is probability of x is less than or equal to 6. Using our calculator again, we get the probability x is greater than or equal to 7 is equal to 0.0001, which rounded to 3 decimal places is 0. Let's do another example together. So in this example, we see that about 1% of the population has a particular genetic mutation. 200 people are randomly selected. Find the mean and standard deviation of the number of people with the genetic mutation in such groups of 200. So a nice little summary of our problem here. N equals 200, P equals 0.01, and Q equals 0.99. So our mean when we're dealing with binomial distributions is n times p. So our mean here is 2. And the standard deviation would be the square root of n times p times q. So that's the square root of 200 times 0.01 times 0.99, which is the square root of 1.98, which equals 1.4. So in example 5, you are looking for the mean of a binomial distribution. Here, n is 700, p is 0.03, and q is 0.97. So your mean is equal to 21. In example 6, you are now looking for the standard deviation. Again, your summary is n equals 700, p equals 0.03, and q equals 0.97. So your standard deviation is the square root of n times p times q. So the square root of 20.37, which is approximately equal to 4.5. So that wraps up our binomial distribution. It's time to talk about our second special distribution for this chapter, the Poisson distribution. Poisson random variables count the number of times a certain event will occur over a specific interval. Some characteristics that you should know is the probability that the event occurs in a given interval is the same for all intervals. The events occur with known mean and independently of the time since the last event. The formula for the probability that x equals x is e to the negative lambda times lambda raised to the x divided by x factorial. Lambda is the mean of the event. E is the mathematical number e, which can be found on your calculator. Now, just like with the binomial distribution, the calculator has a couple functions that can be useful in speeding up the number crunching. So these two useful functions is Poisson's PDF and Poisson CDF. Again, we need to know how and when to use each of these. The probability that x equals x for a Poisson distribution should be calculated on the calculator by using Poisson PDF, lambda, comma, x. And the probability that x is less than or equal to little x should equal Poisson CDF, lambda, comma, x. Again, to find these functions on your calculator, you'll be using the distribution menu, so you'll want to hit second, then vars to get into the distribution menu. These two should be found right around where the binom PDF and binom CDF functions were found. Let's look at some examples. So a certain kind of sheet metal has, on average, 9 defects per 12 square feet. Assuming a Poisson distribution, find the probability that a 19 square foot metal sheet has at least 10 defects. So we need to find lambda. So to find lambda, we're going to take the 9 divided by 12, because it on average has 9 defects per 12 feet. And then we're going to take that times 19, because this piece that we're looking at has 19 square feet. So on average, we should have 57 over 4 defects on this piece of metal. Now we are looking for at least 10 defects. We're looking for the probability that x is greater than or equal to 10. Now again, we're going to have to use our complement rule to rewrite this so that we can use our calculator. And then we'll be using the Poisson distribution. So 1 minus the probability that x is less than or equal to 9 is equal to 1 minus Poisson CDF. Lambda is 57 over 4, comma, x is 9. This tells us that the probability that this 19 square foot metal sheet has at least 10 defects is 0.902. Looking at example 7, a certain kind of sheet metal has on average 3 defects per 18 square feet. Assuming a Poisson distribution, find the probability that a 31 square foot metal sheet has at least 4 defects. Finding lambda, you'll do 3 divided by 18 times 31. This gives you 31 over 6. We're looking for the probability that x is greater than or equal to 4. So you're going to be doing 1 minus Poisson CDF, 31 over 6, comma, 3. This gives you the probability that a 31 square foot metal sheet has at least 4 defects equals 0.758.